Hello everyone, welcome to my presentation. I'm Raymond Law, currently serving as the Assistant Professor in Food Science and Technology program at BNU HKBU United International College, located in Zhuhai, Guangdong, China. In today's talk, I would like to give you a general understanding of my previous and current research on developing and innovating some of the intelligent food packaging materials. Let's first step into the background information related to my research. For developing a food packaging material, what we need to consider is that there's four basic functions. Among these, protection, containment are mostly related to the product itself, while communication and convenience functions are being considered whenever we need to improve the consumer perceptions. So the advanced packaging systems will have to enhance one or more of these functions as listed over here. One of the key concepts related to packaged food product is its shelf life. Every consumer considers the shelf life as essential to be part of evaluating its quality and potential safety concerns. So the shelf life is determined as the time during which all the primary properties of the food remain acceptable. Well, there are three major factors are controlling the shelf life or changing the shelf life by changing the product quality or changing the packaging material, or we may change the storage and distribution environment. As listed over here, the product quality is dependent on these many factors such as perishability. Some of these fresh meat, vegetables are belonging to the highly perishable products, while ice cream is relatively having a longer shelf life, is more or less like the semi-perishable, and some dehydrated foods are relatively more stable, so their perishability is much lower than the fresh meat, vegetables, and fruits. Well, deterioration mode is also essential for developing food packaging materials because this may include the microbial growth, the oxidation of most of the micromolecules in foods such as lipids, proteins, etc. Plus, we would also consider the bulk density and the processing techniques as something that may change our product quality itself. Well, for the scientist to develop a new packaging material, something we need to pay attention is the barrier properties as the first thing that may change the different deteriorative reaction rates because of the intake of water and the gas exchange with the environment, as well as the mechanical properties, so that the packaging material can be able to hold our product with certain physical protection. Well, somehow for the advanced packaging systems, it does involve the potential package product interactions. Last but not least, the distribution environment is also essential. That because of the change of temperature, pressure, and moisture, a lot of the deteriorative reactions will change so that the shelf life may not be essentially as what we predict at the beginning. Okay, so how to display the actual shelf life on the exterior packaging material? This is through the open dating system, which is the legible date displayed on the package. In different packaging systems, we can generally divide this into two different types. One is so-called best before date, which is the last date of maximum quality. That means even after this date, the food itself might be still acceptable, but the quality is not as premium as what we're consuming for this date, before this date. Well, the other concept is so-called expiration date. This is the date after which the food is no longer acceptable. So somehow for the consumers, they may not be able to recognize the difference. As a result, this causes a lot of food wastage because of the misunderstanding of best before date. This is why that the intelligent packaging systems can be further developed so that we can have a better way to monitor the real-time freshness, and every consumer, not only consumer but also all the other stakeholders in the food supply chain, can perceive the freshness of any packaged products in a more precise way rather than just relying on one best before date. So it comes to the intelligent packaging concept. The intelligent packaging is so-called the packaging that contains one or more of the external or internal indicators to be embedded inside the packaging or onto the packaging material that is able to give us something to showcase the history or any quality indicators of the food itself. So basically speaking, intelligent packaging systems are aiming to enhance the communication and convenience functions of food packaging. Let's check out some examples. Uh, RipeSense is a commercial product which is being used to monitor the freshness of different fruits. For example, within this image, what we can see is that they're attaching these colorimetric indicators directly onto the package so that it can monitor the gases environment inside this box of pears. So during this storage period, it is able to change color chemically, and at the same time, we know that the quality of the pears are also changing with a different textural profile. So how to perceive this is to correlate the textural properties of the box of pears corresponding to the different colors. When it's super fresh, it's very hard, so it's crispy. When it changes to firm and to juicy, the color changes from red to orange and to yellowish. Another example is coming from Wander sensor, which is an oxygen indicator that showcases the potential change of color upon the exposure to some high levels of oxygen gas. Well, indeed, within this sensor, the methylene blue was being employed as the indicator compound, which was able to change color with the presence of another reducing agent. Whenever the oxygen gas is exceeding 0.5%, it will change to purple or bluish from the pinkish color. Here it comes to the colorimetric indicator concept, which is specifically important in my research because these are the chemicals are able to change color upon the exposure to different types of environments, such as the change of pH, the change of temperature, the change of chemical reaction, electrical current, or even light exposure. That's known as the different chromic properties. And depending on the chemical properties, we can divide these dye indicators into 5 major categories: the Lewis acid base, Brownstein-Lowry acid base, or solvatochromic, vapochromic, or even the dyes are able to induce the redox reactions and aggregations. Here it shows thermochromic ink as being printed on this Coca-Cola bottle was developed by the market in Turkey. While we can see these ice cubes are able to change color if you're storing them in lower temperatures so that you can see this visual changes. Once the colorimetric indicators are being studied, we may classify them into two major categories, which are either natural or synthetic. The natural colorants, including anthocyanins, betaines, curcuminoids, and carotenoids, these things can be directly extracted from fruits and vegetables, but somehow they are relatively more unstable with the changing environment. The synthetic colorants have many categories. Here are only listing some of those: azo dyes or sulfonphthalates or metal porphyrins. They can have a couple different mechanisms with the color responses upon the changing environment. Well, once the colorimetric indicators are being decided on targeting any specific food products, we may consider the way to fabricate such indicators to develop the indicator materials. These are the basic indicator development methods coming from literature that we can perceive. The most common methods include the direct soaking of the blank papers or cellulose substrates directly into the solutions of emulsions containing our dye or pigment components. While we may also consider the preparations of films, this can be plastic films or even the edible films that are made by food polymers. These films can be produced by embedding the colorants directly into these polymer materials. And we may also consider the production of such indicator materials by electrospinning and preparation of nanomaterials. Here I would like to give you a heads up of a special method on indicator fabrication by inkjet printing, which is essentially used in my research because inkjet printing is a versatile technique for rapid liquid deposition, which is consistent with the industrial packaging operations. We can easily prepare our ink solutions and then formulate the printable inks finally printed on the printing substrates with whatever shape that we wish, such as this fish shape that is able to change color with the exposure to increasing levels of volatile gases. In this case study, we'll check out how these inkjet printed indicators are responding to monitor the freshness of different marine fish fillets. Well, briefly speaking, fish spoilage is related to three major mechanisms, which are enzymatic autolysis, lipid oxidation, and microbial growth. Generally speaking, enzymatic autolysis happens as early as after slaughtering the fish, while oxidation and microbial growth will happen in the latter stage. Well, the spoilage gases coming from different marine fish are mostly related to the different bacterial species as listed over here. We can see trimethylamine. This is the most essential fishy order, plus some other gases or volatile components. We can use this as the potential indicating compounds that would react with our colorimetric indicator. In the first stage of this study, we have tried out the printing of such colorimetric indicator dyes onto a transparency film, and then we're checking out this indicator area's response to the exposure of olive amines. This area of indicator is composed of 9 times 7 of different indicator spots, and each spot is composed of a different formula of the 3 different types of indicator dyes. So for such screening, each individual spot out of these 63 different ones, we can check out at some specific locations the color change towards all of these 6 different types of volatile amine components are relatively higher for these spots. So we could recognize some of these dyes are more sensitive to any of these analytes that can be used for the subsequent study. In the following study, we are also trying the similar types of indicator dyes. Well, in this case, in order to give us a clear color response, we're using the opaque inkjet printing photo paper to be as the substrate. And this is the actual testing cell. The fish fillet is located inside, and these indicators are also stored inside, but they're facing towards the camera, which is located on top, so that we can capture its potential color changes. And this figure just shows us the design color as the actual color strip from the computer, and these are the actual colors that they are printed out because we have already replaced the original inks. These are the actual color responses coming from each indicator strip with the storage time of 7 days at 4 degrees Celsius for 3 different marine fish species: perch, haddock, and catfish. We can see there's a gradual change of color responses for each type of the fish being studied. Following the visual difference of the color responses, we have also conducted the PCA analysis onto the color responses for each type of the fish. We can classify them into different clusters, and most of these clusters are able to differentiate the color responses at a single storage date. We have also tested the correlation in between the color responses of the indicators as well as the chemical deteriorative reaction rates. The top figure is to show us the TVBN changes for all 3 different fishes, and we can see that based on the predicted model, there's a high level of calibration coefficient of variation as well as the high level of cross-validation data. So this can showcase that there, based on the color responses, it can showcase the TVBN changes in a precise format. This would also apply to some other chemical parameters being studied in this research, which is not shown here. Well, some further studies can consider the combination of the colorimetric indicator with the data carrier function that can design a QR code, such as in this case, that has some indicating components inside. Well, besides the major case study that we have just gone through, these are some additional studies that have done in the past to develop the colorimetric indicators for monitoring the gases and also liquids. For example, in this study, we have tried out to develop the actual span nonwoven that contains curcumin as the indicator. The color responses are actually apparent both under the daylight and UV light conditions. I've also included another study that is to test the color responses of monoterpenes in hemp essential oil. That's to determine the color change within the liquid state. These are the actual results, and because the reaction is relatively slow, so we have also studied the acceleration of such reaction by heating the solution up, as shown here. So the above are everything that I would like to share today. Thank you everyone for your attention to my presentation. These are my contact info with the telephone number, the email, and you can also scan this QR code for my web page. If you have any question or concern, you can shoot me a message by email. And at the same time, I'm also looking for potential collaborations. Thank you so much.